Good. Yeah. All right. All right. Thanks, everyone here in Dafar for attending this week's seminar. This week we have an alumni of our department who will be introduced by Professor Igor Bolanov. So, Dr. Bolanov, the floor is yours, and then welcome to our speaker.
Well, welcome everyone to the seminar. Yeah, it is my great pleasure to introduce Dr. Jun Fang. He is my very first PhD graduate at NC State when I started my career. So it's 5 years ago, but yeah, time flies. And so he was actually focusing his research on back at NC State on the thermohydraulics of nuclear reactor channel flows, and was supported by the Castle project. So it was a very exciting time. And he did an awesome job with his PhD and studied a lot of methods. And now he's moving on up a career ladder and continuing in the area. So I think he did a postdoc on the Exascale computing project at Argonne. And now he's with Nuclear Science and Engineering Division at Argonne National Lab. And I'm looking forward to hear what's going on in his research career nowadays. And please welcome our speaker, Dr. Jun Fang. By the way, quick thing, yeah, so if you do have questions, please do post them in the chat. And then in the end, we will try to, I think Professor Shannon will help us out with the audience questions, and then with the chat questions as well. All right, thank you. Please go ahead, Jen.
Okay, all right, thank you for the introduction. I'm glad to be here. So I've been working at Argonne for more than 4 years since I graduated from NC State. I still remember the days coming to Burlington for the seminars. Let me guess, today we probably only have some soda and cookies. I remember back then, whenever there's a big guy giving a seminar talk, there would be a lot of fruit and even pizza or pasta. I still remember those days. So, well, anyways, the topic of my talk today is reactor hydraulics for the exascale computing era. And here you will see, as nuclear engineers, how we prepare ourselves for the coming of exascale computing. And the research I'm going to present is a teamwork involving multiple national labs and universities, and led by Argonne and Oak Ridge. So let's get started. Here's an outline. The work here is funded by the DOE Exascale Computing Project. So I will first give an overview about the project background and its mission, that is to develop the multiphysics simulation capability for nuclear reactor system. Specifically, we're targeting the small modular reactor design by NuScale. And around this mission, in the second part, I'm gonna introduce the development regarding the simulation and modeling capabilities, which include some highlights about our state-of-the-art CFD capabilities. And I'll also briefly talk about the coupling framework, which is Enrico, which bring together the neutronics and CFD. So in the real nuclear reactor core, there are a lot of detailed geometric structures. Even with the exascale supercomputer, we won't be able to resolve all these geometric details. So instead, we will have to develop some kind of reduced order methodologies to model the local effects. And then in the third part, I'm gonna talk about the recent efforts to push the simulations scale up to the full core and make sure they're ready for the exascale supercomputer. And then I will end the talk with some concluding remarks. So what is exascale? An exascale supercomputer means it can perform 1 billion floating point operations per second. So that is 10 to the power of 18. And to put it into a context, the current world #1 supercomputer is this Fukaku supercomputer in Japan, which has a peak performance about 500 petaflops. And the current fastest supercomputer in the US is the Summit supercomputer at Oak Ridge, which has about 200 petaflops, and one exaflops is 1,000 petaflops. So, and we want to lead the game. So we're building Exascale supercomputers. One of such examples is the Aurora being built at Argonne, which has at least one exaflops performance. So as a response to the arriving of this exascale computing era, the ECP was established to accelerate the development of a capable exascale computing system that integrates both the hardware and software for the mission critical and science essential applications. So I also want to clarify here, the ECP will not be responsible to build these supercomputers. Instead, it will drive the pre-exascale application development and make sure the US has a capable exascale ecosystem once the new supercomputer is delivered. So you may ask what the exascale supercomputer can do. So from the traditional, weather forecast and predicting the climate change to simulating the galaxies and even mapping the neurons in the human brain. And among these ECP priorities, there's one specific to nuclear engineering, that is to develop the multi-physics simulation capability for the new reactor system. And as I mentioned earlier, our target is the new scale small modular reactor design. On the right-hand side, you can see a sketch about the SMR system. On the bottom, we have the reactor core. And then in the middle, we have the steam generator. And then on the top, there's some control devices. So why we choose the SMR? So it's because it's very different from the traditional PWRs. So first of all, it's much smaller in terms of the size and power, which means many of the old correlations won't work for this new design. And also, as you may notice, there's no pump in this system. So the SMR is driven by the natural circulation, which requires high fidelity fluid flow simulations. And then here comes the SMR, of which the mission is to couple most accurate available methods to perform the virtual experiment simulations, which includes two primary components. One is the Monte Carlo neutronics, and another one is the CFD with turbulence models. And under this XSMR, we define this challenge problem. So in order to simulate the full new scale SMR core by coupling continuous energy Monte Carlo neutronics with CFD, we need to have a complete inverse Coulomb loop. We will need this accurate turbulence modeling and also the capability to perform neutronics calculations at a pin resolved level. And we also want to study different scenarios, including the quasi-static and also the startup conditions. And in the table on the bottom, so I just show some examples how the individual physics component can benefit from this upgrade from petascale to exascale. For example, in the CFD simulations, on a petascale machine, we can only perform the simulations for single field assembly, but we can potentially scale that up to a full reactor core on the exascale machine. So, so here we just summarize the capabilities needed for the challenge problem we're targeting. So first, we will need a multi-physics coupling framework between the Monte Carlo neutronics and CFD. So within this framework, the neutronic solver will provide the heat source, and the CFD solver, and with conjugate heat transfer here, will provide the field temperature and the coolant density. And we also need the accurate representation of the temperature dependence of nuclear data. And on the other hand, we also need the high resolution CFD modeling of the reactor features. So one option is to do this hybrid RANS and LES. For example, we perform the detailed resolved large area simulation for just one assembly within the full core, and in the meantime, perform the RANS simulation for the rest of the assemblies. And we also want to include models that will incorporate the effects of assembly mixing events on the flow. As I mentioned earlier, we won't be able to mesh the detailed reactor structures even with exascale supercomputers. So we will need some models to take into account these effects. And we also want to include the pressure drop models across the steam generator in the SMR system. Last but not the least, so we also want to make sure these Monte Carlo neutronics and CFD solvers can run very efficiently on the exascale architectures. So, and in the next section, I'm gonna show you the state-of-the-art CFD capabilities we have at the lab, and I will also briefly talk about the coupling framework. So the CFD solver being used in this project is NEC 5000 and NEC RS. So NEC 5000 is the NIM's signature CFD code for high fidelity simulations of fluid flows. So NIMS is a DOE program, and it's short for the Nuclear Energy Advanced Modeling and Simulation. Both the NEC 5000 and NEC RS are based on the spectral element method. It's a subset of the finite element, which kind of combines the flexibility of domain discretization of the finite element method and also the accuracy of the high order methods. So the codes have demonstrated excellent scalability on leadership class facilities, such as Mira Theta at Argonne and Summit at Oak Ridge. So on the right-hand side, I just show you a nice picture about a wire-wrapped SFR bundle. So it's a courtesy from my colleagues at Argonne. So NEC offers a wide range of models, so including the high fidelity direct numerical simulations, large area simulations, and also recently implemented the RANS models. So I want to mention here, for all the new supercomputers being built in US, they are adopting a new heterogeneous architecture, which have both CPUs and GPUs. So in order to make the best use of what the new supercomputers can offer, we have to redesign our CFD code. So here we have, as a result, we have got this NEC RS, which is a GPU-oriented version of NEC 5000 that offers significant speed up on these new machines. So here's some equations. So I don't have a lot of equations in this presentation. So these are the governing equations for the mass, momentum, and energy conservation equations being solved in both NEC 5000 and NEC RS. And here, what I show is for the so-called low Mach number, low Mach model, or Boisnest model, which will be used in the natural circulation problems. So basically, includes the density dependence on the temperature. And I also want to mention here, the temperature is solved as a passive scalar in NEC. And NEC allows you to solve as many passive scalars as you want. So as I would mention later in this presentation, we have the newly implemented RANS models. It's a two-equation K-omega model. So basically the turbulent kinetic energy and the turbulent dissipation rate are also solved as passive scalars in NEC. So one of the essential tasks in the CFD is to generate the colorful figures and videos. So here's a great example from our LES of the sodium fast reactor. It's periodic in the axial direction, and it shows the pressure distribution along the assembly. So basically, NAC 5000 has a very established capability for LES and DNS. And you can find a lot of journal papers, discussing about the benchmarking and validation of LES simulations or DNS simulations done by NAC. And so specifics for the LES model, NAC offers several different filtering schemes. And what I really want to emphasize here is that this p-type refinement. So different from the regular finite element or finite volume codes, NAC has this p-type refinement, which basically equivalent to the mesh refinement in the finite element. So you can just simply increase the polynomial order and perform the simulations at a much finer resolution. And this is another example to show the meshing flexibility and scalability of NAC. So as you may know, the pebble bed is really popular these days, and the company X Energy even got an ARDP award to build their pebble bed reactors by 2027. So X Energy is one of our partners. So in order to accommodate this design needs, we're kind of pushing the limits of CFD. So here we're able to model like a full core of the pebble bed reactor, and the code, the NAC can be scaled up to the entire summit machine. So yeah, this is a great example to show the scalability of NAC. And in addition to the high fidelity LES and DNS, we also recently implemented the RANS models, specifically the wall-resolved unsteady RANS models from the K-omega family. So currently we have the standard K-omega, the K-omega SST, the low Reynolds number K-omega, and also the K-tau model, which is a variation from the K-omega model. And the tau here is actually the inverse of the omega. And here I show a example RANS case for the axial neutron reflector design. So the Reynolds number here is very high, it's 900,000. Talking about the Reynolds numbers, for the typical PWR flow conditions, one can expect the Reynolds number to be about 500,000 in the fuel rod bundle geometry. And because the SMR is driven by natural circulation, the flow rate is smaller. So, but we do expect a Reynolds number of 60 to 80,000 in the fuel rod assembly. So there are also some ongoing efforts to implement the wall functions in NAC, as well as the steady RANS solver. So in addition to the CFD capabilities, I also want to briefly talk about this our coupling framework, which is called Enrico, Exascale Nuclear Reactor Investigative Code. So it's also named after our lab funding father, Enrico Fermi. Basically, the Enrico is a driver application that automates the workflow for solving coupled particle transport, heat transfer, and fluid dynamics problems. So here I show like two mesh, one for the neutronic solver and another for the TH solver. And so basically, Enrico requires the two meshes to be conform, and also it has a efficient communication scheme to exchange the information between the neutronics mesh and TH mesh, basically like copying the heat source calculated by the neutronic solver to the neck, and also provide the temperature from neck to the neutronics. So currently we have two neutronic solvers available. One is OpenMC, another is Shift. And at the CFD side, we basically coupled the NEC 5000, both NEC 5000 NEC RS to this Enrico drive. And also there's also a simple surrogate TH model just for testing purpose. And here's like a detailed structure about the driver application. And so what I want to emphasize here is that the neutronic solver and the CFD solver are coupled in memory. So we don't have to write out any files and then for the communication. And also another strength of Enrico is its extensibility. Currently, we only have two neutronic solver options, but in the future we can also potentially incorporate other neutronic solvers. So if any of you is interested in this multiphysics coupling driver, you can find a lot of details in the journal paper on the bottom. All right, so then we will shift the focus to the flow physics modeling. All right, so the RANS model is relatively new to NEC, and also the NEC RS is basically a new code. Before we conduct our investigations, we want to first make sure the codes can give you the right answers. So we did some benchmarking studies. So the first study is to compare the results from NEC RS and NEC 5000. So basically, given the same boundary conditions and input parameters, we want to make sure the NEC RS can produce the identical results at the NEC 5000, and especially for the fuel bundle geometry we are interested in. So, and they do provide these identical results. And at the next step, we also compared the NEC RANS results with other RANS models and even DNS. So from this law of the wall plot, you can see the velocity profile from the NEC RANS model agrees really well with the reference data. And as for the turbulent kinetic energy, we understand there's some difference at the near wall region, but overall the accuracy is good enough. So in the real nuclear reactor core, like within the assembly, we have these detailed structures. So one of the most important geometric features is this spacer grate, which is used to hold the few rods together, and also the mixing vents are installed on the spacer grate to promote the flow mixing and thus improve the convective heat transfer inside the core. And so in order to model this, the influence of these detailed geometric structures, so we need to develop some dedicated momentum sources. But in order to develop and calibrate these momentum sources, we need some reference data. That's the reason we performed the large eddy simulations for this geometry. So in the figure on the right-hand side, you can see the strong influence from the mixing vents. There's a lot of flow rotation downstream the spacer grate. So we performed the large eddy simulations to generate the reference data, and then use this data to calibrate the RANS models, the momentum sources in our RANS models. So talking about the momentum sources, the formulation we proposed actually are very simple. So there are two important parts. One is this eta, and another variable is this coupling time scale. So basically, we will use the LES data to tune our eta. So for the RANS case, I also show the discretization of the domain for a single subchannel. As you can see, the mesh is much coarser than the LES case, which allows us to scale up the simulations. And on the bottom, by applying these momentum sources, you can see this kind of twisted streamlines in the field rod bundle, which is a clear sign of the effectiveness of the momentum sources. But we also have to make sure we reproduce the right right level of flow rotation in the domain as we observed in the LES with the resolved geometric details. So then how we characterize the flow rotation or the effect of the mixing lens in the LES case. So for that purpose, we define two important quantities. They are the swirling and mixing factors. So one is used to, so basically the swirling factor is the averaged the cross flow magnitude along the diagonal lines here. So basically this quantity is a good indicator of the flow swirling within the subchannel. And the mixing factor is the averaged cross flow along the across the gap lines, which is an indicator of the cross flow between neighboring subchannels. So this way we can extract some quantities and use that quantity to tune our momentum sources and make sure we can reproduce the same level of flow rotation in the RANS case. So here are some results for the swirling and mixing factors and a comparison between the RANS and LES case. So as you can see here, the RANS case with momentum sources can produce the equivalent magnitudes of the swirling and mixing factors. There is some deviation at the beginning of the momentum source application zone, which is expected because in the real design, a lot of space is occupied in the real reactor assembly. But here in the barrel bundle, we don't have that. And also, in addition to the magnitudes, the momentum sources developed are also capable to capture this decay trend, like how the effect of mixing bands reduce in the downstream locations. So here, as you may notice, the swirling factors along two diagonal lines are significantly different. That is actually related to the specific deflection of your mixing bands in the subchannel. So they have this altering pattern for the deflection of mixing bands. And the mixing, we're glad the momentum sources can also capture that subtle difference here. And in the string-wise direction, we also want to reproduce the pressure drop because it's very important and it determines the overall flow rate in the SMR system. So by tuning our momentum sources, we're also able to reproduce the approximately the same pressure drop between the LES and between the RANS and the LES reference. And more importantly, the slope of the pressure or the pressure gradient are the same or very close downstream the spacer grade region. So for the spectral element method, we also want to do the mesh study to see how sensitive the momentum sources are with respect to the mesh simulation resolution. So here, as you can see, with a very low polynomial order, that is relatively coarser mesh, we see larger deviation from the LES reference, but by increasing the polynomial order, we're able to make the RANS results converge to reference data. So here the the actual polynomial order we choose is actually the order of 7, which is actually the sweet spot of NEC, where NEC can deliver like optimized efficiency, and also so it's a kind of a balance between the efficiency and accuracy here. So, and in the next section, I will talk about our recent efforts by pushing this CFD capabilities and coupling framework and to the applications of a full core SMR, and also make sure they are ready for the Exascale. So here, I show some temperature fields from the coupled simulations for just a few rod assembly. So here on the left, you can see the temperature from the solid region, which are basically the fuel rods, and the empty spot here are actually the locations of the control rods. And on the right-hand side, I show the temperature distribution in the fluid region, which is for the coolant. So we observe a peak temperature of about 1050 K in the fuel region, and an overall like about 50 K temperature rise for the coolant. Here are some other key quantities from the coupled simulations. One is the K effective. So you can see the Enrico quickly converge over the iterations. So Enrico actually performed this so-called Picard iterations till the convergence. And then on the right-hand side, I just show the change of temperature at every iteration. Then we move forward. We want to, because the goal is to be able to perform the coupled multi-physics simulations for full SMR core. So here I just show the mesh for the full core. For SMR, there are 37 assemblies in the core, and each core consists of and each core is basically a 17 by 17 rod bundle. So it's a huge mesh, which has about 36 billion degrees of freedom. So here there's a local view for the mesh, and you can see the regular circles for the fuel rods, and also larger circles for the control rods. And here I only show the fluid domain. And we also did a scaling study for this full core MSR case. As you can see, the NEC scales really well on up to the full core, up to the entire summit. And at the entire summit, we still have 70% parallel efficiency, which is good. But I also want to mention NECRS is still under active development, and we expect better scaling results in the near future. And on the right-hand side, I show the distribution of string-wise velocity from the full core. It's because the domain is so large, it's kind of a little difficult to see the local details. And here we also try to apply the momentum sources in the full core. And on the right-hand side, you can see the distributions of these momentum sources or forcing functions. And I also want to emphasize some of the nice flexibility about these momentum sources. For example, you can decide whether or not to apply the momentum sources around the control rods or in the edge channels of the assembly. And you can also decide how many layers of momentum sources you want to have in the vertical direction. Because in the real nuclear reactor, you have multiple layers of spacer grid along the span of fuel rods. And here's a local view of the cross flow in the full core, from the full core simulations. And you can see there are strong cross flows generated by the momentum sources, which is promising. And of course, we will do like more testing of this momentum source application in the full core in the near future. And here, so what I have presented before are only from the full core results are only from the CFD only simulations. And most recently, we're trying to extend the we're trying to extend the multi-physics simulations to the full core as well. So here are just some early results from this effort, and we show the heat source and temperature field from the full core. Well, that's about it. So in conclusion, both the CFD code and the copying driver application have reached the maturity for production simulations of an entire reactor core. So in other words, so these capabilities are already ready for simulations on the new exascale supercomputers. Hopefully, we will see them next year. And in the meantime, the momentum sources we developed can successfully reproduce the key flow characteristics induced by the detailed reactor structures, such as the spacer grid and the mixing vents. So we can reproduce both the flow movement on the lateral or cross-sectional plane, as well as the pressure drop in the streamwise direction. So as a work in progress, there are also a lot of efforts going on right now. So we're testing the momentum sources in the full core model, and we also want to incorporate the momentum source for the coupled multi-physics simulations. And eventually, we want to progressively working towards the SMR design conditions. So for the simulations, you have seen the Reynolds number is actually only like about 10,000, which is still slower from the expected value of 60 or 80,000. So we also want to port these simulations to the new supercomputers. So again, I want to acknowledge the research I presented is funded by the Exascale Computing Project, and also it's a teamwork. And I want to give special thanks to my colleagues from PSU, Argonne, and Oak Ridge. So thank you for your attention, and I'll be glad to answer any questions.
All right, thank you very much for a great presentation. So we're gonna queue up the chat here.
Mm-hmm.
And then also, if participants would prefer to ask their own questions, please feel free to raise your hand, and I can call on you, and feel free to ask a question yourself if you'd like. So first off, is there any questions from any of the in-person participants before we get started? Okay, so as we're waiting to see if anything comes up, I'll start asking some of the questions in the chat. First question from Patrick Hartwell asks, what level of precision is Exascale referring to? Half, single, or double precision?
So it's double. I think for half, the summit can already, perform the Exascale, with half precision. Yeah.
Okay. It looks like Dr. Bolinoff also clarified.
Oh yeah, that's right. Mm-hmm.
So our second question comes from Professor Hayes, who asks, how did you get a random placement of the triso fuel in a pebble bed simulation?
Yeah, so we have there's a Veromi method. So we have a dedicated program that calculate the position of the pebbles for randomly packed pebble bed. Yes.
Okay. Next question is, are momentum source terms added in all the cells, or only in the vicinity of the spacer grids?
So the momentum sources are only added in in the locations where we expect the spacer grid and mixing length to be. So it's not applied to all the cells.
Okay, and in doing that, do you use a structured mesh for the LAS study with spacer grids?
No, it's unstructured. So for the LES reference simulations, we did it with the unstructured mesh. But for the RAN simulation, it's a structured mesh. I hope it clarifies it.
And if there's any follow-on questions for any of the questions that are being asked in the chat, please feel free to post them if you'd like, or raise your hand. The one last question I see here on the chat is there any best practice to extract most useful data and information from the full core simulations?
That's a good question. So I think so here so we let me think, how can I put it this? So for right now, we only extract the range of the design parameters, such as the range of temperatures in the solid region and the temperature in the cooler region. I think it would be very useful to monitor the ranges of these values from the simulations. Yeah, I think that's what we have been doing for now.
Okay. Thank you very much.
If I may, one question.
Sure.
Yeah, Dr. Bolden.
Yeah. So Jun, very interesting, very good presentation. Thank you very much. So for the Reynolds number, when you deal with RANs, I mean, we all know what, when we deal with DNS or LAS, the
right.
computational cost implications. So with RANs, shouldn't it be, I mean, you have to resolve the boundary layers somewhat, but
right.
The bulk mesh is not that, I mean, is it, do you know, like the exponent, computational cost growth, is it the same or is it smaller for RANs as you increase the Reynolds number?
So as I mentioned, the specific RANs models we have, it's the wall resolved RANs models, which means we still have a fine resolution near the wall. And the rule of thumb there is to keep the first layer of mesh of the wall to be under the Y class of 1. And in the bulk region, it's much more tolerant. And I think the overall, like the ratio, the mesh size increase ratio in terms of the Reynolds number is lower than DNS. For sure.
Yeah, you can keep the bulk as sort of coarse. I mean, it's only flatter there, right? It's the boundary layers. Yeah,
right.
Thank you. And another follow-up question. So
that's the reason we're developing this wall functions capabilities to kind of overcome this limitation of wall resolved RANs.
So like better high Reynolds number type of.
Right. So that's kind of the motivation of our wall function efforts. Yeah.
Okay. And the follow-up on momentum sources. Do you have to, and I don't know, maybe I missed something, but as you work at different Reynolds numbers, do you have to completely redesign the momentum sources or remodel them, or the model is kind of universal?
It's not universal yet. We have to do some recalibration if we want to. Actually, I didn't mention in the presentation, we did the LES reference simulations for multiple Reynolds numbers from the basic like 10K 10K to 80,000. So if we need, we can do some interpolation, between the Reynolds numbers.
Thank you.
Okay, last chance for questions from the. We got one from one of our in-person participants. So go ahead.
Yeah, so you showed on one of the slides a reference for people who are interested in the multi-physics coupling between neutronics and thermal hydraulics. Could you go
Mhm.
back to that slide so I can get that?
This one or the one before?
This one, yeah.
Okay.
Good.
I got it. Thank you.
All right. Okay, any other questions? So we got one good, we got a online, we got a face-to-face compliment on a great presentation. So with that, I think there's no better way to close a seminar than with a compliment. So if there's not any other questions, thank you very much for your excellent presentation, and look forward to seeing everyone in Burlington or online or wherever it may be. So take care, everyone. Thank you.
Thank you, Jun.
Thank you so much for the presentation.
Thank you, Dr. Shannon.
Yeah, no comment. Thanks.
Thank you for the coffee, Mario.
Jan, how it's everything in Argonne? Are you happy there?